thank them for inviting me. I don't know where I would talk about this otherwise. I mean, if I were at a conference of people in gravitation, I would have had to give a nice sensible talk. But since this is all about categories and physics, I'm going to take it as a license to be a little crazy. Okay, so what I want to try to explain is that I've believed for several years now that the approach to quantizing gravity that I did, oh yes, thank you, jointly with John Barrett, in order to be completely interpreted, had to be connected with the branch of category theory called model category theory. And the reason for this is that there are just all these profound coincidences, almost like a telephone call from heaven, that between the two subjects, I'll try to lay this out for you and show you the resemblance. Now, I have to say, model category theory is the deepest branch of mathematics I've ever learned. It took me several years to understand. So you'll forgive me that I'm only going to touch on the parts that are important. I couldn't really do justice to the axiomatics of it in 1 hour. But if you actually learn this, and also this approach to quantum gravity, the resonances are just very profound. So, and I believe now within model category theory there's something called localization. If you have a model category, then for any function in the model category, and the function could be the identity from an object to itself, you can localize the category and get a new model category. So you have a natural way of saying two objects are equivalent if they look the same to somebody. So this is a very profound resonance with something that we know in quantum gravity called the Bekenstein bound. That only a finite Hilbert space worth of information can get from a bounded region to the exterior. And I believed, since I was a little boy, that that was the real solution to the problem of the divergences. We have to get rid of the ultraviolet divergences in a real mathematically honest way, even to really understand quantum field theory, and certainly to quantize gravity. And the way to do that was to replace the point set foundation, which has been our foundation of mathematics ever since the first sentence of the first book in mathematics in the world. Set Euclid's Elements, page 1, definition 1. A point is that which hath no part. And we're already in trouble. So every 2,500 years you have to dig up the foundation. So I believed that for a long time, and it really seemed to me that this localization in model category theory was the perfect setting for it. So now, pardon me if this introduction is a little bit complex, it's sort of like a higher order diagram. There was something wrong with this model for about 10 years. And finally, APR and also Levine independently, this one's Rovelli.
Engel, Pereira.
Engel, Pereira, and Rovelli, thank you. Then out here, okay. So they found a new quantization of this. And from my point of view, it was really sort of disgusting that I hadn't thought of it. But it took 10 years. But it resolves all of the interpretation problems. Now, what I believe is that that supplies just what I've been missing. That the connection to to model category theory now becomes rather straightforward. And the sort of interpretation and localization to what's sometimes called holography. Well, that's the physics battle name for Bekenstein's bound. That the amount of information that can be contained in a region is proportional to its area in Planck units, not its volume. So, as I'm going to try to show, there's a very natural way of implementing that. And it does seem to supply the thing I didn't know how to do, to turn this into a model category. So, I want to explain all that to you. I'm afraid it's a bit ambitious for 1 hour, but I think I'm going to do it in 1 hour. So, the objective of this talk is for you to understand the following two conjectures. That is to say, by the end of the talk, you should know what all the words mean and understand some pictures about them, which more or less formulate what I'm trying to say. Don't worry if you don't know the words yet. So, conjecture 1. The new model of quantum gravity describes a bounded region as a vibrant object in a model category. And since I haven't told you what a vibrant object is, let me give you the intuitive thought that this means a sort of a thickening. As I've said in print, I believe that quantum gravity teaches us that space-time is like a piece of paper. At large scales, it looks like a manifold. Looks like a two-manifold. But of course, if you examine it below a certain critical scale, it has a very complicated structure and larger dimensions, but it doesn't change its homotopy type. So I believe that is what the quantum theory of gravity that we've evolved really tells us. I'll try to show you why I think that and what it has to do with category theory. Anyway, the technical term for that is vibrant object. That's a very basic thing in model category theory. I couldn't tell you the full axiomatics of a model category even in a whole hour. The most important part of it is that things have vibrant models. I'll try to explain that. Which is a quantization of the Sullivan model. So obviously, I have to tell you what the Sullivan model is. It's a very standard construction in model category theory. The important thing about it is that Dennis Sullivan wanted to extend model category theory not only as a foundation for topology, but also for geometry. That was his point of view from the beginning, and so this construction allows us to transport geometry from point set topology to these model categories. As of course I will explain that, but then conjecture 2, the EPRL quantization Introducing model. Makes is a functorial extension of the CSW TQFT. So we can think of it as a richer structure built on three-dimensional TQFT by adding more structure categorically. This supplies holography and implements conjecture 1. Okay, so that's the picture. And in fact, since we will generalize this, it also opens a completely new avenue to looking for unified theories, things that are extensions of gravity, because it now becomes something where we can start with the TQFT and then enrich it. And that's a whole new way to approach trying to find richer structures that include gravity. And it hasn't really been looked at yet. This is a new idea. Okay, so that's the objective of this hour. And of course, when you build a bridge, if you don't already have a bridge, you have long delays running back and forth across the river. So I'll have to go back and forth until I try to meet in the middle. So let me begin by telling you something about model category theory. Okay, so the idea again is that we don't really believe all this stuff about point set constructions. You see, there's actually two good reasons. One is in physics, that we don't believe that there are points because there's a minimal length that can be measured. And when you do quantum field theory and embed it in R4, all the integrals diverge and you have to do all kinds of monkey tricks to make sense of it. And they don't work quite as well as we'd like to pretend. So the foundation is still mysterious. You can find, for example, in Feynman's book, the suggestion that in order to really solve the problems, we have to find something that's something in between discrete and the continuous. The other thing is math. Every time a mathematician says that the expression, the real numbers, is telling a lie. There are many different models of the real numbers. Theorems that are true in one are false in another. And nobody knows what the real numbers are. I don't know what the first real means in that sentence. I'm not even quite sure what the second real means. I mean, if real doesn't mean that it refers to nature, then I don't know what real is. But, so the foundations of mathematics are in the same state as the foundations of physics. They work until you look down. So you learn not to look down. So, I've believed for a long time that the resolutions of these two things come together, that mathematics is something we abstracted from nature, and if the continuum isn't working out quite the way we like, we have to go back to nature to understand what to do. So the suggestion is that even though the spaces are not well defined as underlying point sets, we don't really know what we mean by those things, relationships between spaces make perfectly good sense. So, I don't know what I mean by the real line, and I don't know what I mean by the circle, but I know what I mean by the winding map from the real line to the circle. In other words, the maps between spaces still make perfect sense, and it's the whole category of them that makes good sense, rather than each one making sense independently as the same infinite point point set that you can never name. Okay, so model category theory isn't a branch of logic, though. It's not like Topo's theory. It's really math. It's really topology. And the reason is that the models that people construct for the category of spaces turn out to be computationally superior to point-set topology. For instance, we can calculate the rational cohomology of the loop space of any sphere on the back of a postage card. We do it by replacing the sphere by a model, applying the operation that gives you the loop space, and then computing its cohomology. We couldn't do it at all if we insisted on mucking around with all those horrible points. This is one of the things Sullivan discovered. I mean, I should warn you that this subject was good for two Fields medals, Quillen and Sullivan. It's very, very deep stuff. It's surprisingly little known among physicists. Well, I shouldn't say it's surprising. But the thing is, the category is the thing of spaces, or some category of spaces where you throw away some of the information in order to be able to get your hand on what's left, like category of rational spaces. These things can be constructed several different ways, and there are functors, pairs of adjoint functors connecting them. And as soon as I looked at this, I said, oh my goodness, this has got quantum mechanics written all over it. They're complementary descriptions, like what John Bias said earlier about adjoint functors looking an awful lot like adjoint operations. So in classical quantum mechanics, you connect position and momentum by adjoint transformations. I bet there's some way of turning the Fourier transform into a pair of adjoint functors. I haven't thought about it very hard. But so now in particular, I want to give you two, and this is the thing that made Sullivan so famous, among other things. I mean, he's a very great mathematician. But so you can have simplicial sets. You can think simplicial complexes. The definition is very abstract and very beautiful, but the thing about it that's so magic is that it has finite models. That's what makes it work. And on the other hand, you can take differential graded algebras. And so how does this work? Well, you take a simplicial complex. Each simplex is given with coordinates. It's a standard simplex, it's got coordinates. So you know what you mean by the polynomial differential forms on each simplex. And you glue them together into an algebra. That's called the Sullivan algebra. So that's like the generalization of the differential forms on a manifold, but it's from a simplicial complex, or simplicial set. Polynomial differential forms. And now you can go back. So you have this algebra. You might have a set here. And you might have the algebra attached to the set. It's a differential graded algebra. And you can go back. And the way you go back is by taking the set of all homomorphisms of this guy into the polynomial forms on a standard n simplex. And then those things glue together to form a big complex. So this way you go by taking A, S, let's say A sigma n, and then you get this small level. And that's the idea. Now, if you go over like this and then back, you get something much bigger. It's like all the simplices that anywhere algebraically related to the initial thing. So that turns out to be this great big thickening of the original space. So this is a great big space, but the way you know where you are on it is by certain functions on each simplex that act like coordinates. You ask, where are the generators of this algebra coming from? And in fact, it's enough, you can use these guys to find cohomology, right? You can calculate cohomology from forms. So it's enough to take generators to the cohomology ring and ask where they go. That's what's called the minimal model. And then you ask where each of those are on the simplex, and that tells you where you are. So these labels on the simplex, which are forms, are telling you where you are in space. So that's the Sullivan algebra. That's I think you can get the essential flavor of model categories. Now, isn't this just screaming out to be quantum theory? Look, you've got one description that's like local, and one that's like, it's like particles, and one here that's like functions on the whole thing. That's like waves, and you've got these adjoint functors that connect them. Doesn't that sound like quantum theory to you? So, that's what I thought. Now, the other thing about this, let's see, what else did I want to tell you? I'm good. No, okay. Now, I want to relate this to the state sum model. Now remember, in the old, take section, state sum models as vibrant objects. So I'm not going to go through all the details of the old DC model. The main idea was, first place, you can describe the geometry of a simplicial complex by describing the bivectors on the faces. Instead of using vectors, we used bivectors. And that turned out to be a good idea because they're amazingly easy to quantize. The bivectors are like you can identify them with the dual of the Lie algebra, and so there's a way of quantizing that with the coadjoint orbits. Or equivalently, you can think that the generators of the Lie algebra are operators on it, so you have to quantize it, and then what you get is representations of the Lie algebra. So the classical picture, we're describing geometry by bivectors, two forms. The quantum picture is now we're labeling the suckers with representations, because that's like a quantization. We're summing over that, and we did some other nice tricks. And it works better than anything else that's ever worked in quantum gravity. It's finite. Actually, it's got a nice Hilbert space now, and it works lots better than, for instance, string theory, which is not finite at all, despite a great deal of folklore on the subject, and isn't even well defined, even perturbatively. But this is actually turned out to be finite and finite triangulation. So we have now a sum over labels, and then the product of some stuff, and the product of 15J symbols on each for a simplex. Blah, 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 blah. Now, what I want to say to you is, we want to think of the different labelings as different places. We want to do this very standard thing whenever you've got a categorical object. You associate to a category the nerve of the category. It's this great big thing where you take all the diagrams and jam them together and make a great big simplicial complex out of it. Okay, we want to do the same thing for state sum model. So all the different labelings are different places. Why are the different labelings different places? Because they're going to look like they're in different places. Because the different labelings are corresponding to different geometries for the region. So let's say that we just did this at a bounded region. We can treat the outside classically. You've got this bounded region here where something very energetic is going on. So it's Metric is quantum, it's some superposition in classical metrics. So what would you see if you had real powerful eyes who could look there? Well, you would see all the parallel worlds sort of superimposing. If you just stood in one place, they'd all jumble together. But if you move your head from side to side, they slide past one another. Because they have different curvatures. So as you move, the parallax changes differently, and you see these different parallel worlds with all their little matter, and the matter is correlated with the geometry. So they would have different little histories going on in them. As you move your head around, they slide past one another. So you would have to interpret that as saying that the region looks like it's thickened. Okay? It's like you have many parallel copies of the region, and they're different places. If a place isn't where a thing looks like it is, then I don't know what a place is. So the relational places of this, as you move you hold it up, there's lots more of them down at this fine scale. That's the thickness of the piece of paper. Okay. Now, in the old model, so now you see how similar this is to the Sullivan model. Instead of labeling things with forms to tell you where they are, we're labeling them with representations, which are quantizations of forms. Now, there's one thing missing from this picture, which is the glue. We've got all these layers, but a vibrant model is supposed to have the same topology. So you need to be able to interpolate between these different labelings, these different worlds. So I worried about that for a long time. I knew something was missing. Something was always missing. And then I learned about the new model. Or, I don't know, is it a new quantization of an old model, or is it a new model? Professor Rovelli told me in an email that it's just a new quantization of the old model. I don't know if he'd say the same thing in print or not. Anyhow, there's so the representations we were using were representations of SL2C, which we learned about from Hari Chandra and Gelfand back in the 50s. Now you can decompose them as representations of SO3, and they form ladders. You get one of each spin in a ladder. Now, one thing they did was to add the inertia. Did I spell that right? Oh, good. So, it's called gamma. It's a term which has no effect in the classical theory of general relativity, but they think you ought to add it in because it affects the classical theory, and there's this general sort of rubric in quantum physics. You have to put everything in unless this is something that makes you leave it out, because the Feynman diagrams will add it in anyhow for you. So anyhow, on that principle, it really ought to be added in. So then with that, you see, we didn't just have this nice tensor category. The old model, we had rep SL2C, and these are the irreducibles here are RK. Rho, there's one continuous parameter and one discrete parameter. It's because the what you would call a new torus is the function complex plane. So it's one Fourier transform and one Fourier series, if you like. So this is rep SL2C, and it contains something that we call the balanced representations, which was R0 rho, and or RK0 rho. So the subcategory set in it, So it never fit very elegantly in the picture of categorification. Now the new model, you include this gamma, and now you get R, K, K, gamma. So you get only a discrete category instead of a continuous one. And this is sitting inside SL2C. But that's the wrong way to think about it. You see, you've got one of these for HK. And in the physical interpretation, you're thinking of them as representations of SO3 and using them to build up space. And then you're adding in time. So the right way to think of what you've really got is you've got what I call a time functor. The physicists didn't say this. I said it. The time functor so it's F sub gamma from rep SU2 to rep SL2C. Now this functor, well, I told you what it does on the irreducible objects. It's a semi-simple category, so the morphisms are easy. They're just multiples of the identity, so it's pretty obvious what that does. Now, it doesn't have a trace, though. This doesn't have a trace. These things are infinite dimensional. So you can't say what it does with the trace. It even has duality of it. But it has two important properties. And these two properties are formalization of what the physicists actually did. They're what makes the model fly. So one, it's co-lax, which means that R1 tensor R2 is included F of So this is what you need in order to figure out which intertwiners to put in the tetrahedron if you already know the story. So it's collax, and it's amply renormalizable, which is to say, although there isn't a trace, there is a trace which you can write down formally, which has a nice renormalization that doesn't destroy any of its symmetries, that works for sufficiently many diagrams that you can do the theory. I mean, you write it as a multiple integral over the big group. You throw away one of the integrals and presto chango turns out finite. This was originally observed by John and me, and then John and John pushed it farther and found out the class of diagrams where it worked. And it still works now, even though we're not doing balanced representations. It works much the same way. So it's what I've called Claren functor. So having formalized that, it's good to write things down in categorical form. The physicists didn't think to do it, but in the first place, it sets it in a broader context and we can see what to connect it to. And in the second place, it tells us how to generalize it. So we could try finding other similar theories by finding other Claren functors. So, what's the point? So now we have this functor, F gamma, from rep SU2, so just ordinary spin, the kind you guys use, to rep SL2C. I wonder if somebody shouldn't at some point try using some of the Gelfand functors and the Gelfand representations and some of the things we do in information theory. They are infinite, but are nice renormalizable traces on them. It might be worth looking at. Just a thought. So now you have two tensor categories, This one is associated with TQF3D TQFT, CSW TQFT. This is associated with 4D B-wedge-F theory, which is a 4D TQFT. So you see now, a new model appears to us as a functorial link between two topological theories. As a three-dimensional side and a four-dimensional side. Now, this works out really, really nice because you get a nice Hilbert space. That was one of the things that was wrong. The Hilbert space in the old model was too small because we quantized strongly instead of weakly and this is, we should have. The only thing I'm doing here is I'm representing the constraint as the image of a functor. I think it's the natural thing to do. Now the point is, there's this old theorem that the Chern-Simons state is a solution of Einstein's equation in quantum gravity. Let's do the Kodama. I made the observation first, but you snooze, you lose. Okay. So, let's explore the consequences of assuming that the whole universe is in the Chern-Simons state. That is to say, it's tied together at the level of space by topological field theory in 2 + 1 dimensions. Okay, now we can reinterpret the EPR Hilbert space They said, suppose you have a three-dimensional triangulated space. The Hilbert space is the space generated by the set of all spin networks you can put on the tetravalent graph, which is dual to the triangulation. So, one vertex in each tetrahedron, 4 edges coming out, one in each face. And you put all possible spin nets on that. That's the Hilbert space. Well, I've seen that before. Went back back before the fall of the Soviet Union. Back. When I got interested in constructing three-dimensional topological field theories. You start out with a triangulated manifold, and you put a 4-hole sphere in each tetrahedron, and glue them all together. And you get a big old surface. It's called the Heegard surface of the manifold. And then you look at all possible ways to label it, and all ways to put intertwiners between them on the trinions. And that was the vector space attached to that, and then I was able to use that to get the invariant 3 manifold. This is one of the standard ways of constructing Chern-Simons-Witten theory. And if you just think about it, if you just take Mr. Rovelli's diagram and fatten it up into a surface, you realize it's exactly the same thing. The only difference is if I want to get a topological theory, I pass to a quantum group. But that would be a pretty natural thing to do, actually. The sort of folklore is that there's a cosmological constant, and one way of dealing with that is to pass to the quantization of the group. So, if we believe that for a minute, as the Hilbert space of sigma of M3, where sigma of M3 is the Heegard surface. to say than to draw, pardon me. Thing I just said. So that means we've got this surface sitting there, and it's got a vector space on it. And that's the vector space that the EPRL model associates to the three-manifold. But they would still probably have pressed, say, that you just sum over all triangulations, which is a shame and a crime, because we've got all these miracles making everything finite. The whole theory is finite. Then the physicists come along and say, oh, sum over all triangulations. It's just formal again. I mean, it's just like they've been dealing with infinities for so long that they feel lost without them. No, I don't think that's good. We want something finite, something that naturally cuts itself off. And I don't believe for 1 second that if you have two triangulations that are almost exactly the same, they're just parallel, they're just different Feynman diagrams that just come over. I mean, they're just slightly different descriptions of the geometry. So what I want to suggest is that we only do experiments in bounded regions. So if you have a bounded region with its interior, we only do experiments in bounded regions. How would we do an actual experiment in quantum gravity? We have some gigantic collision, either because we're trying to make a tiny black hole in order to make a starship, or just we were having some particle experiment. We want to calculate the quantum gravity effects, even if they're negligible. We might just want to count them for fun. Okay, so there's this tiny region where something's going on, and out here you can just safely treat everything classically. That would be what a real experiment in quantum gravity would be like. It's just like any other experiment. You don't do experiments in the whole universe. It's too big. It takes too long. Can't get outside it to look. Okay, so you do an experiment like that. You've got some triangulated region. And then the Heegard surface of the triangulation would be some higher genus surface that met these holes here. Okay? But now, the boundary would be some triangulated region, and it would have a representation of SU2 on each hole. So, the formulas of topological field theory tell you how to associate a Hilbert space to the boundary. It's actually very simple. You just tensor all those representations together. Think of it that the quantum geometry of the boundary is described by some finite set of observers at Planck scale, and they can only observe a finite amount of information each, which is represented by this finite dimensional representation. You know, you can represent representations of SU2 as fuzzy spheres. You can take the sphere and you can collapse its L2 of the sphere down to some finite subspace, and that would give you the representation. It's the whatchamacallem theorem. What's theorem? It's two people's. Okay, I don't know. Anyhow, so you can think of the boundary as a whole bunch of fuzzy spheres, and that's all the information that can come out of the boundaries, what all those little guys can see coming out. Okay? So that's a description of the quantum geometry of the boundary. And all the information you can see is what comes out through there. Anything that you can see has to come through the boundary. And the dimension of this Hilbert space, it's the tensor product of all those guys. And those things are like punctures in quantum gravity, so they're in loop quantum gravity, so they're units of area. So the dimension of the Hilbert space goes exponentially with the area, which means the entropy is proportional to the area. So it implements the Bekenstein bound. See? This interpretation of the quantum theory, you get a natural model for Bekenstein's bound. So I conjecture that's Hilbert space spends all the information that can come out. Now, because we have a topological field theory, we've got more then vector spaces on surfaces. We've got vector spaces on surfaces, and what else? A little bit on, what is it? It's late, everybody's asleep. What else do we have? Vector spaces on surfaces, and, oh, you know. Oh, come on! Operators for cobordism, of course you do, see? Just need a little encouragement. Okay, I've been teaching in Kansas too long, sorry. So the region between the boundary and the Heegard surface is a cobordism. So we get a linear map from the Hilbert space of the Heegard splitting to the Hilbert space of the boundary. And it's only the image of that we have to predict, that outside, if we do an experiment that tells us something about the geometry of the region, that's all the information we ever get to see. It's the Bekenstein bound. So we have many different triangulations. They're all getting mapped to this same boundary, and because they're being mapped by a TQFT, it's consistent. Map one to another, the composition works. That's the axioms for TQFT. So what have we got? We've got a localization. We're only interested in the information that can flow through the thing on the boundary. So we get a model category with a localization. And you remember the one thing I told you was missing to make the thing a fibrant object? It was the glue. We had to be able to fill in simplices. I mean, Sullivan did that when that was one of the hard things. He showed that you could always extend forms from the boundary of a simplex to the interior. There was this very delicate lemma that was the key to this whole thing. But now we can do it because we're identifying these things with states in this one Hilbert space. So that means we have a superposition. So if you have two triangulations that only disagree at one point, they're going to be states that interpolate between them. So you see, a sufficiently rich triangulation could sample the whole thing. You could do the whole theory on just one triangulation, and that would be everything you'd see with respect to the Bekenstein bound. And if you had two triangulations, they aren't just juxtaposed, they're complementary. And if you looked at this thing, you would see all these parallel worlds. But beyond a certain point, it would be like Rashomon. Remember the movie Rashomon, where you could look at the same thing and see it several different ways? Because of the limits on information, at a certain point you could say, well, this happened superposed with this, or maybe on the other hand, that happened superposed with that, and there's this limit on information that's sort of gravy, so I can't tell. So that's what it would be. That's what it would look like. It would look like what it is. It would look like a fibrate model. It would look like a thickening of space-time. You could see it by moving your head around, only there's a limit on how much information you can get. So that's really still sort of a conjecture that the thing I get on the boundary, I mean, it's the right dimension to be the Bekenstein bound. And if we're in the Chern-Simon state, you could probably make a sort of a formal argument that you would recover the topological theory. So a state here could only be related to its image under the linear map there. So the finite theory, finally really well-defined theory, resolving all the funny ambiguities about the triangulation, and constructing the model category, all come together. And the new model just had the tool that we need. Now, what I haven't done yet is worked out how this is consistent with time evolution. Now, I have the feeling it ought to be, because we're getting everything from a functor. It's a Clairaut functor. The tensor product is compatible, and the things you need to form in space-time can be renormalized in an isometric way to get finite things. So it embeds it inside the depth theory. So there should be some higher compatibility that you could actually show it's consistent with time evolution. And also, we would like to think something about how light propagates through this. And since it has a semi-classical picture, where John and his crew have developed enormously, so it's a superposition of classical geometries, and it's easy to see how light rays go through classical geometries. There should be some way of actually working out the information flow and seeing that this bound is actually satisfied. But if it is general relativity, there should be this bound. I mean, when you put too much curvature, nothing should get out. That's the whole reason why there's this Bekenstein bound. If it's not true, it's not really quantum gravity. So there should be some way of checking that. That's a whole lot more work. There should be some way of checking the time evolution. That would be a whole lot more work. And I said everything I had to say, and I'm 4 minutes early. And so thank you very much for your attention. Everybody can have dinner now. So that's all I have to say. Yes?
How far are your conjectures from being set?
Ask me again in a year. I was writing this on the plane. I just got this a few weeks ago.
So there's nothing published yet?
Huh?
So there's nothing published yet, could we know this?
I will get it on, okay. I have a preprint. I was a little hesitant to put it on the internet, but it will get on the internet in the next couple of days. So if you just Google my name, it'll be on GRQC in a very preliminary form in the next couple of days sometime.
Well, there's lots of stuff you need in the meantime to warm up. So.
Yeah.
There's lots of work on the EPRL model.
Yes, it's a very good, actually, John did some really nice papers on the Lorentzian version, which is what I'm talking about here. Yeah, other John, yes. And, monocategory theory. There's a lot of books with that title. Actually, the books on rational homotopy theory are good because these two guys actually give you the rational homotopy theory. When you do this construction, you throw away all the torsion part of the cohomology. So, yeah, there's plenty of things to read. I actually think model category theory is just this wonderful subject. And it's got physics written all over it. Okay, other questions? No? Yes?
Yeah, given that John Barron and you stopped at the same point, we have now these two talks here. What's the relation between them? These beautiful black holes. It's sort of static both of them.
Well, okay, so it's very interesting. He was thinking about enriching the algebraic structure that goes into quantum gravity to include not only categories, but also functors including categories. And that's the exact same thing I just said. We've got a space category and a space-time category. We build up space out of its symmetries. We build up space-time out of its symmetries. And there's a functor between the two categories, and that's what we use. So some places we just use the first category, sometimes we use the functor, sometimes we use the big category. So there's something very reminiscent about the two things. And I don't know about the particles yet. I don't know how to put particles in here, but I mean, the easiest thing to do would be to just try a fancier topological field theory. But maybe the right answer is to try, we've got two categories and one functor, now why stop? So that seems to me like it dovetails very much with what John was saying.
Does the functor have a left adjoint?
Sorry? Sorry.
Does the functor have an adjoint?
Does the functor have an adjoint?
So we just
Yes.
we just talking about induction and restriction?
Yeah, well, no, it isn't induction.
No, it's not induction.
No, this is a new functor. It's what I call the time functor. And it has a parameter gamma. It associates to each irreducible the irreducible k gamma k. So you get it strings it out in a diagonal in the parameter space of that's the simplicity constraint with the inertia parameter in. So it's a little bit funny. I mean, it's certainly a function. It's no problem at all what to do with morphisms. But the tensor product is a little tricky because the tensor product is a direct integral on one side and a direct sum on the other. So what it is sort of a singular thing. It's like an improper object. It's a sum of delta functions in the integral. So there's probably more. It actually lives in some suitable completion. So there's some more delicate work to be done with that. And then there's the renormalization ability, which we already know about. So that's the start. So this is not a familiar functor. Now, would it be an adjoint to? I mean, there's an obvious restriction, which is that you can take each thing. Now, but you see, the natural thing to go back when we're down. I mean, the obvious thing is to take a representation of SL2 and just take a forgetful functor. But then you get this big sum. It's a ladder. This thing is just taking the bottom level. It's taking each thing and mapping into its bottom level. And there's very clever physical arguments about quantization that tell you that's actually the right thing to do. I mean, the argument which originally Rovelli and company it comes very naturally out of thinking of these things as quantum geometry. So I haven't really worked out the adjoint functor, but there's a natural thing to try.
Yes, I have
Question back there?
So I'm not a split here. I'm trying to have a drink with them. So they assure me that loop quantum gravity has no chance of being finite if you put in matter. I was wondering how you react to that.
Matter? Well, loop quantum gravity in and of itself doesn't have matter in it. Well, this isn't exactly loop quantum, but I mean, that was the whole issue we were just exploring. How do we get the matter? I mean, string theory is wonderful if you get any combination of particles and fields except the ones we see in nature. If you get millions and millions, and you would think it was almost impossible that you could have that many possibilities and not the one we see. I have an interpretation of string theory that I call the hole in the plate theory. That every other theory except this one was possible. They all happened, they canceled out, and that's why we saw this one. That's the best interpretation of string theory I've ever heard. But, okay. Well, I mean, if it was good whiskey, I'd probably drink with them too. But loop quantum gravity in and of itself, it's certainly true, doesn't tell us how to add the matter. Now, there are several interesting approaches. One is that not all the triangulations need to be manifolds. They could have conical singularities. So you could try to explore the geometry among a conical singularity. I proposed this a few years ago, but it was very vague then because the model was so well formed. I intend to come back to it. That's one thing. Another possibility is to look at richer topological field theories and see if they give us matter. Another thing is to say, since after all matter just doesn't live in the same place as geometry, it's supposed to live on paths, maybe we need a third category. Or maybe there's some natural further morphisms of categories. Or, there's this world algebra thing that Kahn talks about, and the world algebra is the same as the quantum group looked as an algebra, and then the representations of that naturally give you the standard model. It's just a little prodding. So that's another possible direction. I don't know how to get the matter in it yet. But I think it's better to be worrying about how to get the matter in it than to have too much matter and try to worry about how to get rid of it. Okay, so any other questions? Okay, so I'd like to thank you all for your attention, for staying awake this late, and thank the organizers again for what was a very enjoyable meeting.